Hey guys, welcome to The Explainer. Grab your notebooks because I am absolutely pumped to be your mentor today. If you're a first-year physics student currently staring down the barrel of IIT JEE Prep, consider this your ultimate high-yield roadmap for mastering atomic structure and quantum mechanics. We're going to break down the dense math, untangle the complex theories, and honestly set you up to just crush those problem sets. I mean, we all know everything around us. The screen you're looking at, the coffee in your mug, it's all made of atoms. But when you really get down to it, what is an atom actually made of? And maybe more importantly for your physics journey, why did our classical, totally intuitive understanding of it just absolutely break down at the start of the 20th century? Understanding that failure is really the key to unlocking the strange, fascinating world of quantum mechanics. Okay, so let's dive into this. Here's the game plan for today. We're going to start with Rutherford's flaw, move into the quantum shift, and hit Bohr's atomic model. Then we'll tackle the dual nature of electrons, the quantum mechanical model, and we'll wrap it all up with electron filling rules. You know, to make memorizing all these formulas way easier, you really just need to understand the story behind them. Like back in 1911, Rutherford discovers the nucleus. That leads to these massive quantum leaps by Planck and Einstein, which actually paved the way for Bohr's discrete orbits. And finally, boom, 1926, we get Schrödinger's wave equation. Seeing how one guy basically fixed the flaws of the guy before him makes the underlying math make perfect sense. All right, section 1, Rutherford's flawed nuclear model. Let's start right at the beginning of our modern understanding, 1911. Ernest Rutherford does his famous gold foil experiment, blasting this incredibly thin gold foil with high-speed, positively charged alpha particles. Now, it was a massive success in one big way. He discovered the nucleus. He figured out that atoms have this tiny, super heavy, positively charged center packed with nucleons, protons and neutrons. But, and listen up because these are classic IIT JEE trap questions, his model had some fatal flaws. See, classical physics says a moving charged particle has to continuously lose energy. If that were actually true, Rutherford's electrons would just spiral inward, crash right into the nucleus, and completely destroy the atom. No way, right? Plus, this model totally failed to explain hydrogen's discontinuous line spectrum. So basically, Rutherford's collapsing atom proved that classical physics just couldn't handle the atomic realm. We desperately needed some new rules. Which brings us to section 2, enter the quantum world. So Max Planck steps up and theorizes that energy isn't some continuous wave. It's actually delivered in these discrete little packets called quanta. His formula is E equals h nu, where energy is proportional to frequency multiplied by Planck's constant. And then Einstein takes this and just runs with it for the photoelectric effect. He states that the maximum kinetic energy of an ejected electron is exactly equal to the absorbed energy, h nu, minus the threshold energy, h nu 0. Seriously, identifying that threshold frequency, that absolute minimum energy required to knock an electron loose, is a super critical concept you've absolutely got to grasp for your exams. All right, section 3, Bohr's atomic model. Okay, so we've got the quantum foundation laid down. Now, a brilliant physicist named Niels Bohr steps in to mathematically fix Rutherford's crashing electron problem. Just look at the difference here. Notice the fatal continuous spiral of Rutherford's model compared to Bohr's brilliant solution, stabilized discrete orbits. Bohr basically postulated that electrons revolve only in very specific circular orbits where their angular momentum, mass times velocity times radius, is an exact integer multiple of Planck's constant divided by 2 pi. So mvr equals n times h over 2 pi. I mean, can you imagine realizing everything you knew about physics was wrong, and this one single equation just fixes it? Because as long as the electron stays in one of those permitted discrete orbits, it radiates 0 energy. No spiral, no crash. The atom is officially stable. Now, as an IIT JEE student, these derivations are absolutely gold for your calculations. You've got to lock these in. Notice the variables, z for the atomic number and n for the orbit number. The radius of the nth orbit, that scales with n squared over z, times the constant, 0.529 angstroms. Velocity scales with z over n. And total energy is negative 13.6 times z squared over n squared in electron volts. When an electron jumps between these orbits, the emitted radiation, your delta E, is calculated using that same exact 13.6 constant. Memorize exactly where those z's and n's are, whether they're squared and if they're sitting in the numerator or the denominator. It'll save you so much time. And seeing how electrons jump between these orbits helps us finally understand hydrogen's line spectra, the exact puzzle Rutherford couldn't solve. When an electron jumps from a higher orbit, N2, down to a lower ground state orbit, N1, it emits very specific frequencies of light. If that electron drops all the way down to N1 equals 1, that's the Lyman series, which emits ultraviolet light. Dropping to N1 equals 2, that's the Balmer series, which gives us visible light. Paschen is N1 equals 3, Brackett is 4, Pfund is 5, and those last three are all hanging out in the infrared region. You're definitely going to want to use the Rydberg constant equation to calculate the exact wavelengths of these jumps.
Moving right along, section 4, the dual nature of electrons.
So Bohr's model was fantastic for hydrogen, but it kind of fell apart for bigger atoms. We have to ask ourselves, wait, what if electrons aren't actually just tiny planets orbiting a sun like Bohr thought? In the 1920s, two massive ideas completely shattered that planetary model. First, French physicist Louis de Broglie proposes wave-particle duality. He equated Einstein's mass-energy relation with Planck's equation to prove that any particle with mass, m, moving at a velocity v, actually has a measurable wavelength, lambda, equal to h over mv, meaning electrons act like waves. And then Heisenberg drops his uncertainty principle. He states that you literally cannot simultaneously know an electron's exact position, delta x, and its exact momentum, delta p. The uncertainty of both of those multiplied together has to be greater than or equal to h over 4 pi. Bohr's perfect, exact circular orbits simply cannot physically exist if we can't even know exactly where the electron even is. Which naturally leads us to section 5, the quantum mechanical model. Because an electron is this weird hybrid of a particle and a wave, we needed a whole new mathematical model, one that embraces probability rather than absolute certainty. Enter Erwin Schrödinger in 1926. His wave equation officially replaces Bohr's absolute 2D orbits with 3D mathematical probabilities. Now, it's a super complex differential equation involving 3 space coordinates, total energy, potential energy, and this amplitude thing called the wave function. But for your purposes right now, just understand the core takeaway. We are no longer calculating exactly where an electron is. Instead, we're calculating the mathematical probability of finding an electron in a specific region of space around the nucleus. To keep all these probability zones organized, we use the 4 quantum numbers. Think of this as basically the ultimate address system for an electron. The principal quantum number n tells us the main energy level and the overall size. Then, the azimuthal quantum number L denotes the actual subshell shape. So if L equals 0, that's S, 1 is P, 2 is D, and 3 is F. Remember, L always ranges from 0 up to n minus 1. Then we have the magnetic quantum number, M, which gives us the specific 3D orientation, varying from negative L to positive L. And lastly, the spin quantum number, S. This one's easy. It just tells us if the electron is rotating clockwise, so plus a half, or counterclockwise, minus a half. And finally, section 6, rules for filling electrons. So now that we have this awesome address system, how do we actually build an atom from scratch for all those chemistry and physics problem sets? Well, here are the 4 rules you're going to use constantly. Step 1 is Aufbau's principle. You always fill orbitals in order of increasing energy, starting with 1s, then 2s, 2p, and so on. Step 2, to figure out that exact energy order, just use the n plus L rule. An orbital with a lower n plus L value simply has lower energy. Step 3 is Pauli's exclusion principle, which dictates that no 2 electrons in an atom can have the exact same set of 4 quantum numbers. If they're sharing an orbital, their spin absolutely has to be opposite. And finally, step 4 is Hund's rule. For your p, d, and f subshells, you have to singly occupy each orbital before you start pairing any electrons up. Honestly, mastering this exact sequence turns calculating electron configurations into an absolute breeze on test day. We've traveled all the way from Rutherford's crashing, spiraling electrons to Schrödinger's crazy complex waves of probability. And yeah, it might seem kind of strange that at the most fundamental level of reality, things are just so uncertain. But I want you to think about this. If the exact position of an electron is physically unknowable, how does mastering its probability empower you to unlock the rest of the physical universe? Because it totally does. The equations we just went through today dictate how molecules bond, how lasers actually fire, and even how the microchips in your computer process data. So when you're tackling your IIT JEE problem sets tonight, keep that in mind. You aren't just memorizing formulas. You're literally decoding reality itself. All right, thanks so much for joining me on this explainer, and I will catch you guys in the next one.